Do you know, researchers have cooled antimatter to near absolute zero for the first time by capturing it in a magnetic trap and blasting it with concentrated laser light. Yes, you heard it right, finally they cooled antimatter to reveal some of the universe's biggest secrets. Many of us think antimatter is just a science fiction topic, but we are wrong. It's real and most expensive substance on Earth. We cannot capture antimatter in space and bring it to Earth. The reason for antimatter so expensive is the technology involved in creating it. The European Organization for Nuclear Research Super Collider is the most complex piece of machinery ever constructed by humans. It took about a decade to construct, at a cost of about $4.75 billion. The collider has a total operating budget of about $1 billion per year, and also consider the fact that it has been estimated to take 100 billion years to produce 1 gram of antihydrogen, that is antimatter. In 1928, British physicist Paul Dirac wrote down an equation that combined quantum theory and special relativity to describe the behavior of an electron moving at a relativistic speed. This theory led to a surprising prediction. The equations that described the electron also described and required the existence of another type of particle with the same mass as an electron, but with positive electric charge. The discovery of such a particle, called a positron, in experiments soon confirmed the remarkable prediction of antimatter in Dirac's theory. Antimatter is the opposite of matter. More specifically, the subatomic particles of antimatter have properties opposite to those of matter. Apart from the fact that antiparticles have different signs on all charges, such as electric and baryon charges, matter and antimatter have the same properties. A particle and its corresponding antiparticle must have identical masses and decay lifetimes. A collision between any particle and its antiparticle partner leads to their mutual annihilation, giving rise to various proportions of intense photons, gamma rays, neutrinos, and sometimes less massive particle-antiparticle pairs. Standard model physicists suggest that an equal amount of matter and antimatter was created during the Big Bang. By rights, they should have annihilated each other in the first few seconds of the universe's existence, leaving the cosmos full of bright light and little else. And yet here we are, so are planets, stars, and galaxies, all existing and exclusively made of matter. Every galaxy, star, planet, and collection of gas and dust that we've found is made of matter, exhibiting the exact physical and chemical properties familiar to us here on the also made of matter planet Earth. Antimatter is more common than you might think. It occurs in thunderstorms, radioactive potassium decay in bananas and humans, solar flares, PET scans, and black holes. But the question remains, where did all the antimatter vanish? Astronomers search for antimatter in space, but it is hard to find and further bring it to Earth. So, to study it and unravel the mysteries, physicists have to make it themselves. And because antimatter annihilates in a flash of energy when it interacts with matter, storing it presents a challenge. The antiproton decelerator, AD, is a unique machine that produces low-energy antiprotons for studying antimatter and creates antiatoms. To actually create antimatter, scientists focused on the simplest form of matter, hydrogen. A hydrogen atom consists of just one electron and one proton. This means that the simplest form of antimatter, an antihydrogen, is made up of an antiproton and a positron. The positron is attracted to an antiproton in the same way an electron is attracted to a proton. The first antihydrogen was made in 1995 at the European Organization for Nuclear Research Super Collider by colliding antiprotons with xenon atoms. This collision produces a positron, which is electrically attracted to another antiproton, subsequently forming antihydrogen. Unfortunately, it only takes a few millionths of a second for antimatter particles to come into contact with their matter counterparts, annihilating themselves and giving off energy. Because of this, scientists have worked on ways to make antimatter stable enough to be contained. The key was to slow the antihydrogens, to keep them from colliding, and this was achieved by containing the antimatter in a bottle at just half a degree above absolute zero, the theoretically coldest achievable temperature. In 2011, scientists were able to hold produced antihydrogen for over 15 minutes using this method. Now in its second phase, the Alpha project tinkers with antihydrogen atoms, literally, a positron orbiting an antiproton, just as an electron orbits a proton in regular hydrogen. Slowing down the motion of antiatoms allows us to perform more precise measurements on its properties. In daily life, you can imagine things moving fast are harder to see than things moving slowly, said Makoto Fujiwara, a particle physicist with Canada's Tri-University Meson Facility Particle Accelerator team. Fujiwara said, the antimatter atoms must be held in an extremely high vacuum in order to prevent them from annihilating with residual gases. When trapped, the antihydrogen is moving fast, just over 200 miles per hour. To cool the anti-atoms, the researchers had to design a laser system themselves. Since they cannot use any conventional dye laser, they had to design the laser system from scratch using nonlinear crystals. The researchers used the bombardment technique, called laser cooling, to slow down the anti-atoms. They bombarded the anti-atoms with photons, or light particles, shot from a laser. Antimatter manipulate happens without destroying it by exerting force from laser light onto the anti-atoms. Once the photon hits the atoms, it excites the atoms, but it also changes their motion, said Takamasa Mamas, an atomic molecular spectroscopist affiliated with the project and who built the laser. At such extreme cold, it was easier for researchers to take stock of how the particles behaved. Better understanding such behavior could provide insights into what happened to all the universe's antimatter. How does antimatter respond to gravity? A long-burning question of particle physics. Soon we will get answers to some of these mysteries.